Hey everyone, welcome back. In this video, we will try to understand how to train a large language model using KTO optimization. Preparing a training dataset for KTO optimization is very simple when compared with PPO and DPO. For KTO optimization, the dataset contains three columns as we have seen in our last video. We have a question column, answer column, and a label column. If label equal to true, we call that question answer pair as desired question answer pair. If label is false, we call it as undesired question answer pair. So now for any desired question answer pair, I anticipate that my actual reward should be higher than my average reward. For undesired question answer pair, I anticipate that my average reward should be greater than my actual reward. Let's try to solve this by taking one question answer pair as example. Let's consider the first question answer pair. How do we calculate loss? Because this is a desired question answer pair, I anticipate my actual reward should be greater than average reward. So that's the reason I consider this equation. So now let's assume that all the lambdas and betas are equal to 1 for simplicity. So now my loss equal to 1 minus sigmoid of z minus z naught. So now how do you calculate z? Calculating it's pretty straightforward, right? You give a question answer pair. You give this question and answer to this reward model. It will generate some value. Let's assume the generated value is 2.5. It's equal to 1 minus sigmoid into 2.5 minus z naught. Now, how do you calculate z naught? Z naught is nothing but average across all the rewards for, I'm sorry. It is nothing but the average of rewards across all the possible answers for a given question. So now for this question, we might have tons of possible answers. We need to calculate rewards for all those answers for this question and average all those rewards. It's a very time consuming process. So we don't do it. What KTO paper proposes is a biased estimate for this Z naught. What it tells us, from this main batch of data, extract a micro batch. So now let's assume this is that micro batch, right? This is that micro batch. So now in this micro batch, create a new column which is called as mismatched answer. How do you populate the data in this mismatched answer? Just by shifting one row upwards. So when you say what is the best programming language, mismatched answer is USA. From where I got it? I got it from here. Likewise, for question, where is New York? What is mismatched answer? It is leave me alone, right? Where did we got it? We got it from here, right? So for this mismatched question answer pairs, you calculate R1, you calculate rewards for each of these mismatched question answer pairs. You calculate reward for this question and mismatched answer. You got to calculate rewards for this question and mismatched answer, which is R2. Likewise, calculate R3. Now I can say that Z naught equal to R1 plus R2 plus R3 divided by 3. I can say that this is my bias estimate of my average reward, right? So KTO paper also introduces something called as a clipping function. And what is clipping function? This is not the final Z naught. It says that Z naught equal to max of 0 and this Z naught, which is my average reward, which is R1 plus R2 plus R3 divided by 3. So this is my final Z naught. So for every row in this micro batch, I will be having same Z naught value, right? So once you calculate Z naught from this, you plug this value over here. That's how you calculate loss for a specific point, right? So why this clipping function is very important. Now let's assume in the nth iteration, my model has become very intelligent. If my model has become very intelligent, my Z naught value will be very less, right? Why? Because it's nothing but average reward. So if you calculate all these rewards, so the reward for a question and mismatched answer pair will always be less. My online probability will be less. So that's the reason Z naught will also be less. If Z naught is very, very less, now let's assume in the nth iteration, I have a true question answer pair. And this answer, though it is correct answer, but it is not great answer, right? Because it is not very great answer, in order to reduce the loss function, it's enough for the Z value to be slightly above Z naught, right? Though my answer is not so great answer, if the answer is not so great answer, right, my Z value will be slightly lesser, right? If you have a great question answer pair, then my reward will be very, very high. If you have a not so great answer, a not so great question answer pair, my Z value will be slightly lesser, right? So now, because my model is already intelligent and my Z naught is much more lesser than Z, right? Even then, even in this case, even my answer is not so great, just because my Z naught value is very less, my Z minus Z naught value will be more. If this will be more, it reduces my loss. So this is not correct. That is the reason we clip this to zero. Even when the model becomes intelligent, right? When my average reward value will be very, very less, let's say it's minus. So that's the reason we clip it to zero. So that if we get not so great answer in future, if we wanted to reduce our loss, my Z value should be above Z naught. If Z naught value is very, very less, even if the reward of not so great answer is slightly above Z naught, we, still loss will get reduced. So to avoid that, the paper has added a clipping function over here, right? So, and this is what is mentioned in the paper over here. Let's quickly go back. Yes. So here they have very clearly mentioned how to come to the KL estimate, which is nothing but an average reward. So here they've talked about mismatched pairs, and they talked about the clipping function over here. You can just go through it. I think pretty much for this video. See you in the next video.